Welcome back to the lectures on chemistry and introduction to molecular spectroscopy. We shall continue the lecture from the harmonic vibrational spectroscopy of a diatomic molecule to look at one model for the anharmonic vibration, and this model is due to Professor Philip M. Morse from MIT around 1929. He came up with the molecular motion being anharmonic and the vibrational motion eventually leading to, for very large frequencies of vibration or very large energies of vibrational quantum number with very large quantum number, the molecule eventually dissociating. In the harmonic model, dissociation does not exist because no matter how high the energy is, the parabolic nature of the harmonic potential energy curve tells you that the molecule eventually reaches back to its equilibrium state, and therefore, there is nothing called a dissociation or a breakaway of the diatomic molecule accounted for in the harmonic model. Therefore, it is very important for vibrationally induced dissociation of chemical structures that the vibrational motion be anharmonic. And the model that was proposed by Philip Morse has the following form for the potential energy as a function of the distance from the equilibrium. The Vr is given by the specific functional form, a constant dE multiplied by this particular mathematical quantity alpha exponential of minus alpha or minus Re whole square. Okay. So, the potential energy has a very specific form due to exponential, and alpha is a constant, which we shall see in a minute how it is identified with the equilibrium or with this what is called the harmonic oscillator frequency. Okay. Now, it is important to visualize this potential energy first to understand why it was why it is meaningful. Now, if you plot V of r as a function of r, it is dE times 1 minus exponential of minus alpha or minus Re whole square. Therefore, at r is equal to Re, the equilibrium bond distance, V of r is 0, because this becomes 1, because this the exponent is 0, therefore 1 minus 1 0, therefore V of r is a minimum at r is equal to Re. Okay. And for very large values of r, V of r, as r goes to very, very large values, or say the limit being infinity, you see that the exponential of minus alpha times r, approximately Re is too small, and as r goes to infinity, this goes to 0. Therefore, the potential energy Ve becomes dE, which is a positive constant. Therefore, for very large values of r, if we go back to the graph, and as r increases from the equilibrium value, you see it is exponential of minus alpha Re. Therefore, the potential energy, and this is a square, this is a square. Therefore, as r is slightly different from Re, this whole graph sort of goes up, and eventually it reaches a plateau, and the value which does not change for very large values of r equal to Re is the asymptotic value, okay, which you can call this. This graph reaches the asymptotic value, and that value is dE. Okay. For R less than Re, this is negative, and therefore the exponent of the exponential becomes positive. And if this becomes more negative, then this increases forever, and therefore what you see here is that. Okay? So this is the form of a potential energy for a given value of alpha. If alpha is very large, then you see that this graph is narrower. If alpha is very small, this graph is more elongated. Therefore, the alpha gives the spread roughly between what is called the harmonic area. This area looks more like a parabola, and therefore you can see that for small values of R minus Re, this function will actually become parabolic in the limit of R minus Re being very, very small, and at R equal to Re, this is the minimum. Therefore, this is the parabolic potential which you have with the half kx square, half k R square that you use for the harmonic oscillator model. It has that as the limit of small amplitude oscillations, and for very large amplitude oscillations, you see that the molecule is such that the atoms go far apart from each other, they never come back, and this is the dissociation limit. Okay? For this potential energy with this form, if you write down the Hamiltonian as minus h bar square by 2 mu d square by d r square plus the dissociation energy dE times 1 minus e to the minus alpha r minus Re squared. The wave functions h psi n is equal to E n psi n has actually closed form solutions, that is analytic solutions, given by Philip Morse and later corrected by Professor ter Haar, that En is h omega E times n plus a half, and there is another term which contains a small constant called the anharmonic constant xe, but with n plus a half whole square. So you can see that the energy level E0, for example, is half h. Let me not write WE. I think we have been using it for angular frequency. So let's write this as nu E and nu E. Okay. Then En for E0 when n is 0 is half h nu E minus, remember this is 1 by 4 h nu E xe. What is the next energy level for this problem is n is equal to 1. E1 is 3 halves h nu E minus, this is 3 half, therefore it's 9 by 4 h nu E xe. Please remember, for motion very near equilibrium, the xe is a small constant and it's called the anharmonic constant, and therefore the energy is not precisely half h nu, but it's slightly lower than half h nu. Xe is positive. Okay. Therefore, you see that the energy levels as you go from 0, 1, 2, 3, etc. are more and more away from what is called the harmonic oscillator energy levels. So if you look at the harmonic oscillator energy levels, if you write that, it's, suppose you call this as E0, and then this is E1, and this is as E2, and compare that with the potential graph which goes something like that. What you see is the lower level is, the lowest level is slightly lower than the original E0. This is E0 because it contains this minus half h x e nu E, minus 1 by 4, sorry. And then the E1 is even lower than the harmonic value of E1. E2 is even closer, and E3 is closer, and so on. And so finally you see that the energy levels become very dense. and so on. Now you can see that as you go further and further up, if the oscillation is sufficiently large, if the amplitude of the oscillation is fairly large and the quantum energy levels are very high, you see that the molecule eventually breaks down and dissociation takes place. Therefore, the energy differences which in the harmonic oscillator model were identical between nearby levels are not so in the case of the Morse oscillator. This energy level is slightly more than, this difference between the two energy levels E0 and E1 is definitely more. If you call it as delta E1, then this is more than delta E2. Therefore, the frequency at which the molecule absorbs, if it is an anharmonic molecule and if it satisfies this anharmonic model, this frequency of absorption is slightly more than this frequency of absorption, and therefore what you see here is of course a spectral line corresponding to delta E1. Okay. If this is the increasing E, the next is the delta E2, if you see it, is slightly lesser than the delta E1. And of course the intensities will also decrease because the higher the energy level is, the fewer the molecules are at any given temperature, subject to thermal equilibrium conditions, and that's a Maxwell-Boltzmann distribution law. Therefore, you see that delta E2, if this is called delta E2, and then delta E3 is even smaller and so on. But something else also happens. In the harmonic oscillator model, it's not possible for us to actually undergo a transition, actually force the molecule to undergo a transition from E0 to E2. This doesn't exist. It cannot be seen. The dipole moment operator does not connect to that. However, in the anharmonic oscillator model, in the Morse oscillator model, it is possible for you to see this transition. It is also possible for you to see, let me put it on a medium point with some other color. It is also possible for you to see this transition. It is possible for you to see this transition and even this and so on. And these are vibrational overtones. There is no overtone in harmonic oscillator model. There is only one line. What you see is only one line corresponding to this delta E, and that's the same for every other transition as well. Therefore, the Morse oscillator provides you a slightly more realistic, what is called vibrational spectroscopy and the vibrational spectrum that you see in the case of diatomic molecules. But please remember, we have kept the rotational motion completely out of this picture. We assume that the molecule is purely vibrating and we do not worry about the rotational energies associated with that. But after we do the microwave spectroscopy, we will see how to look at the vibrational rotational spectrum together. But for the time being, the simple picture of the harmonic oscillator model gives you no transition other than one line. The anharmonic model due to Morse oscillator gives you several energy levels which are different from each other, and therefore the gap between them is also different. So let's calculate that gap for a simple example. Say E0 was written as h nu E minus 1 by 4 h nu E x E. E1 was written as h nu E 3 by 2, sorry, this is half h nu. This is 3 by 2 h nu E minus 9 by 4 h nu E x E, and E2 is written as 3 by 2, so then it's 5 by 2 h nu E minus 25 by 4 n plus a half whole square. Therefore, it's 5 by 2 whole square is h nu E x E, and so on. Therefore, if you calculate E1 minus E0, the answer is h nu E minus 9 by 4 minus 1 by 4. So, you get 2 h nu E x E. X E is a very small number, therefore, this is an extremely small number compared to h nu E. Okay. Essentially, you can write this as h nu E times 1 minus 2 x E, x E being very small, this is close to h nu E. But what about E2 minus E1? If you look at that, That is again h nu e, but the difference is 25 by 4 minus 9 by 4. Therefore, you get 1 minus 4 x e. Okay. The difference is 16 by 4. And the next one, if you want to write, is minus 7 by 2 h nu e, and it is 49 by 4 h nu e x e, and therefore, you see E3 minus E2 is h nu e times 49 minus 25 is 24, therefore, you get 1 minus 6 x e. See how the successive energy differences are becoming smaller and smaller due to the larger contribution of x e. This is minus 2 x e, here it is minus 4 x e, and here it is minus 6 x e. Therefore, it is possible for us to actually obtain values for nu e and x e if we get two experimental spectral lines. If we get a transition due to this and if we get a transition due to this, then the two equations involving the nu e and the nu e x e can be solved, and it is possible for us to obtain numerical values for the unharmonicity constant, and therefore use it for fitting experimental spectra of diatomic molecules where the motion is slightly unharmonic. There are molecular problems where the motion is very, very highly unharmonic, and in the case of polyatomic molecule, we will come to look at least for a brief moment, what are called non-rigid molecular motions and so on. Therefore, it is important to understand that vibrational spectroscopy starts with the elementary model of a harmonic oscillator, but then the corrections to the harmonic oscillator and the real molecular spectrum are usually taken into account by correcting the potential energy in such a way that unharmonic corrections can be done. In the previous lecture, I mentioned the unharmonic corrections can be x cube like terms, the potential energy terms that you have here, that is r minus re cube terms, r minus re to the power 4 terms, and so on. They are called cubic unharmonicities and quartic unharmonicities, and the r minus re square is called the quadratic harmonic term. So keep this in mind in solving some of the problems related to unharmonic vibrational motion of a diatomic molecule. In the next lecture, we will continue this and look at polyatomic molecular motion, and then in a similar way, we will extend the harmonic oscillator model to molecules with many vibrational degrees of freedom, what are called the normal modes of vibration. We will also some pictorial representations of some of the normal modes of vibration through a calculational tool that is quite well known today called the Gaussian 09, the Gaussian program. And the Gaussian program is a computational chemistry program which allows you to calculate molecular properties quite accurately. We will see the harmonic oscillator model for a polyatomic molecule in the next lecture following this. Until then, thank you very much.